Welcome. In this session in linear data analysis, we'll explore the Gram matrix, which is one way that we can use to handle vectors that are embedded in a higher dimensional space. Let's make an observation, which is first about mathematics and then about data. Mathematically, one of the things that we found useful in looking at the singular value decomposition was what we called the right transpose product of a matrix, and that was just the matrix times its transpose. Well, when we do this, what we find is we can compute each entry ij, and that would be the ith row of A times the transpose of the jth row, or we could think of it as a dot product. And if we have data, this may be a little problematic, but we'll continue and we'll imagine that we can do it for data also. So now what happens when we embed those data into a higher dimensional space? Well, we would have the embedded matrix of our data, and then we would multiply that by the transpose of the embedded data. And what we would find is that that would then be the embedded ith vector is, we're writing that as the embedding function phi of the ith original data vector. And then we'll take that, this will be the transpose, and that will be the transformed or embedded row j transpose, and that equals a dot product. So what we can do is observe from this that when we're computing A transpose, or when we're computing A hat transpose, in either case, if we want to compute the entire matrix, what we end up doing is either transpositions, or we can also think of it as doing dot products. Now, let's take a look at this in slightly more detail. So what we'll do is we'll define, in the extra notes for this class, we go through the full mathematics, but we'll say a kernel function is, and we'll write that as a symmetric function. So I'll use script k, and if we have a row-like argument u and a row-like argument v, that this has to be symmetric, and what that means is that if we reverse the order of these and we pass first v and then u, we end up with the same result. And if we have finite data, and I'll write these as, let's say that row I of our data, it has all real numbers and there are n entries, then if we compute a matrix K as, if we say that the ijth entry of K is this kernel function of, now that'll be row I, row j, if this matrix by construction has to be symmetric, and if it is positive semi-definite, we'll say then this function is a kernel function, and we'll say that K is a Gram matrix. And this is named after the mathematician Gram, who we also might realize is the same Gram as in Gram-Schmidt orthonormalization. So let's take some examples that we've already gone through. So example one was we took a row that was 2 dimensions and we embedded that as u1, u2, and what we did was we said we'll take this as, I'll just write this as u1 squared plus u2 squared, and that's the squared norm of the original observation. So what does its kernel function look like? Well, we can say that if we hand it observation u and observation v, that it will be what we can do is we can say, what would the dot product be? So we'll say that is the dot product of the embedded U and the embedded V. And that dot product is symmetric. So what will that work out to be? Well, if I take the dot product of this with U's in it and this with V's in it, that would be U1 V1 plus U2 V2 plus U1 squared plus U2 squared times V1 squared plus V2 squared. And that's simply taking this and doing a dot product of a U and a V. And when I work that out, what I see is this part, I can write that as U dot V. And then after doing some multiplication and simplification, what I see is that this product term is actually the dot product of those observations squared. So what I can do is I can compute the dot products of these embeddings, and I don't actually have to do the embedding. All I have to do is this particular computation on the original observations. Okay, so let's now try our other embedding was U1, U2, and we embedded that as U1 squared, U2 squared, and then this other term was the square root of 2 times U1, U2. And now let's find its kernel function. So that would be kernel function given observation U and observation V is going to be the dot product, and now that will work out to be, that will be U1 squared V1 squared plus U2 squared V2 squared, and then when I take the dot product of this against root 2 V1 V2, that will be plus 2 times U1 V1 U2 V2. And I'm just reordering those because then I can see immediately that what that will be is that will be the dot product of the observations squared. And this is why we sometimes refer to this kernel function, this particular embedding, as being a polynomial embedding. It's because it's a polynomial function of the dot product of the observations. In this case, it's just the quadratic, but you can now imagine that we could take any power whatsoever. Now, as we take powers, what will happen is the size of this embedding will undergo a combinatorial explosion. But the computation of taking the dot product of the original observations and raising them to a power is something that we can compute very fast, and it takes almost no additional memory. So now, with this understanding, what we can do is we can say we could compute entry ij of A hat transpose as, and we could just say that that is going to be a, that will be the kernel function of observation I, observation j. And we'll gather these, into, so much of the literature refers to this as K. What we'll do is we'll call this a generalized weight matrix. So we'll gather these into, and we'll call that generalized weight matrix W hat. And we will require that this generalized weight matrix has to be symmetric by definition and has to be positive semi-definite. And so what we can do is we can then perform So let's ask this is, can we perform PCA on this generalized weight matrix? And the answer is yes, and that is, let's put that in capital letters, yes, and this is called the kernel trick. So there are a couple of versions of the kernel trick depending on which algorithm, but this is the kernel trick for principal components analysis. Now you're probably wondering, perfectly reasonably, what are some kernel functions? Well, there's an infinite number, but in data analysis we see a handful that are frequently used. So typical kernel functions, we'll define them in terms of rows, but they can also be defined in terms of vectors, is if we have a pair of observations and we just take the inner product of those observations, that's called a linear kernel. And that really is what is happening with all of our data analysis in PCA up till now, is we've been using what would be called a linear kernel. The quadratic kernel that we're exploring is we could take the inner product of the two observations, we could add 1 to it, and we could square it. So this is a special case of a quadratic kernel. A general polynomial kernel looks a lot like it. What we can do is we can take the inner product of our observations, we can add a hyperparameter c, and then we can raise this entire scalar value to the power L. And this would give us an order L approximation. If we were to try to do the embedding of u and v would be combinatorially exploding in terms of the number of variables and the order, but this computation is really concise. Another kernel that we often see used is called a Gaussian kernel, and this is a generalization of the normal distribution that you may be familiar with from statistics. The Gaussian kernel is computed by, we take the difference between the observations, we find the squared norm, we negate it, and then we divide it by 2 times a hyperparameter sigma. If your data were distributed normally, you would think of sigma squared as being the variance. For us, sigma squared is often another hyperparameter that we have to provide or adjust. If we're working in MATLAB with data that are standardized, the MATLAB will simply take the difference between our observations, find the squared norm, negate it, and perform the exponential function. Now, if you were trying to embed data using, for a Gaussian kernel, what you would need to do is each of these observations, you would have to, for each one of the terms in these observations, for each variable, you would need to expand this Taylor series, and usually for typical data and their representations, you'd have to probably use about 1,000 terms. So you'd get this enormous explosion in space and therefore in time, but if you use a kernel function, it's concisely and easily calculated. So now, what can we use this for? Well, we derived PCA, or Principal Components Analysis, using the scatter matrix of variables. What we'll have to do in our next lecture is we'll explore a scatter matrix that uses observations. And this is now a bridge. The Gram matrix is a bridge to something called kernel PCA. The idea is we'll use the Gram matrix in place of a transpose, which will be our scatter matrix for observations. And how does this work? Well, what we'll have to do is we'll have to explore how this works, and we'll have to explore how can we center embedded data in a concise manner. So, what have we learned in this lecture? Well, we're now able to relate an embedding to a kernel function. At least for certain embeddings, we'll be able to find a kernel function. We can now select a kernel function from a library of kernel functions, and we now know how to compute a Gram matrix from given data.